This is lesson 28, VHDL example 15. And in this example, our goal is to write a single VHDL program called X7seg, which will be a component that we can use to display a 4-digit hex number stored in X15 down to 0 on the 7-segment displays. We'll also make another version called X7seg-B, which will display the 4-digit hex number with leading blanks. Okay, well, here's how we do it. We have a X7seg is going to look like this, which is very similar to what we had in the last example. The only difference is we've replaced the buttons we had here with a 2-bit counter. And this 2-bit counter is going to count S here, 0001, 1011, to multiplex the 4 hex digits in X. We'll also have to modify our AN code so that when this is 00, then we select only digit 0 by bringing AN 0 low, and so forth. We're also going to add a new input to this AN code called A-enable so that we can control if we display anything on a particular digit. That is, if A-enable 3 down to 0 is 1111, then all digits will be enabled. That is, when we display hex 1, 2, 3, 4, they'll all be on. If we want to turn one of the digits off, we will just put a 0 in the corresponding digit position here. So we can make any of the digits that we want to be disabled. So the question is, how do we do this 2-bit counter? Well, we'll see in a minute how to do that. We're going to need an external clock, and your FPGA board has a 50 megahertz clock, but that's way too fast to control our counter here, because we want to count relatively slowly, maybe say 190 hertz, because each digit's on a fourth of the time, and so 190 divided by 4 would be about 48 hertz. And if you refresh each digit at a 48 hertz rate, then your eye will integrate it and it'll look like they're all on at the same time. So we'll need to have a big clock divider really to cut the clock frequency down to something manageable. We'll see how to do that in a minute. All right, let's write the VHDL program then. Our X7seg is going to have a 16-bit input X for the 4 hex digits. It's going to have a clock and a clear. That's going to be for our little counter, we'll see. Then our usual A to G out, our enable out, 4 bits, and our decimal point out. Okay, here's the architecture. We need a signal S, that's going to go into the multiplexer, 1 down to 0. Our signal digit, that's the output of the multiplexer, input to X7seg. Our A-enable, that's new, that's 3 down to 0. That's going to be used to enable each of the 4 digits. And now we have this clock div, which is 20 down to 0. This is going to be a 21-bit counter, and we're going to peel off, as we'll see, the top 2 bits. So our S signal here is going to go into our multiplexer. That is, the 2 control bits for the multiplexer are just going to be clock div 20 down to 19. Now, we're not going to talk about counters in much detail, because we cover those in detail in later lessons after we've learned some sequential logic and how flip-flops work. But for now, you just need to know that we're going to have a 21-bit counter, and the top 2 bits, if this clock, this 21-bit clock, counts at a 50 megahertz rate, then the top 2 bits will count at about 190 hertz rate, which is what we want. So that's where S is going to come from. We'll set A-enable to 1111, decimal point to 1. This is our quad 4 to 1 mux that we had in the last lesson. We're going to do it exactly the same way, just make these processes. Here's the 7-segment decoder, we still have to put the AN code module in. Okay, so now we have to write a process for this AN code module. Now remember what this does. AN enable, if they're all ones, we'll set them all to ones here. That'll enable all of the digits. So if it's enabled, then if S is 0, 0, we want to bring AN to 0 to 0. If S1, 0 is, say, 1, 1, we want to bring AN 3 to 0. So look how we do it. There's a little bit of a trick here. We'll set the output ANs to 1 to begin with, all 1, 1, 1, 1. And then if the corresponding bit, A enable, is set to 1, then we'll make the corresponding AN to 0. Now there are two things to look at here. First of all, S, you remember, is of type standard logic, and I'm writing AN sub some subscript, which I need to be an integer. So, for example, if S is a 1, 0, I need to convert it to 2, and you do that with this function convert integer. So convert integer S converts, say, 1, 0 to 2. So if A enable sub 2 is equal to 1, then AN 2 gets set to 0. The other thing to remember is that these assignment statements don't get executed, you remember, until the end of the process. That's why we can set AN to 1, 1, 1, 1 to begin with, and then if one of the corresponding A enable inputs is 1, we set that corresponding A enable bit to 0. That will override this first one because it hasn't been actually executed yet because we're not at the end of the process. So when you get to the end of the process, you'll have all of the ANs 1s except one in which the AN enable, any of them in which AN enable is equal to 1. The only one left then is our counter. Here's how the clock divider works. Remember we had the signal clock div, and we set S to clock div 20 down to 19. That gave us our low frequency count. But how did it count to begin with? Well, that's this clock div signal. And the way it works is we say if clear equals 1, we set them all to 0. This others go to 0 is a way to set all 21 bits of these to 0 if the clear signal input is 1. Else, now this funny clock tick event and clock equals 1 means that if on the rising edge of the clock we increment the clock div by 1, that is, we make it a counter. So this is how we make a counter. Don't worry about these details for now. We're going to come back and talk about these in later lessons in more detail. But this is how we get the counter to work, and we set S to the upper 2 bits to get the low frequency counter to work. So that's X7 seg. To test it, we'll make a top level design. M clock is the name of the 50 megahertz clock that's going to be coming in here. That's in the UCF file. Then we have the usual button, A to G, AN, and decimal point. And here's the component X7 seg. We'll display A, B, C, D all at one time on the 7-segment display, and we do it just by port mapping X7 seg. So X goes to X, clock goes to M clock. Clear we'll put to button 3. A to G goes to A to G, AN to AN, decimal point to decimal point, and that's it. You can download this and check it out. We'll make another version called X7 seg B, which will display leading blanks for leading zeros as blanks. And the way to do that is easy. We just set our A enable 3 down to 0 for leading blanks. For example, AN3 is just going to be set to X15 or 14 or 13 or 10. In other words, if any of the top 4 bits in X is set to 1, then AN enable is 1, and otherwise it's 0, and if it's 0, it will be displayed as a blank. Similarly, if the first two digits are 0, leading zeros, that is, if x15 or 14 or 13 or 12 or 11 or 10 or 9 or 8, if any of these are 1, then we display it. If they're all 0, then we display a leading blank. And similarly, A enable 1, we have to check all the first 12 bits, and if any of those are 1, we display it, otherwise we display 0. AN enable 0 is set to 1, so digit 0 always gets displayed. There's the quad 4 to 1 mux, same as before. This is the same as before, our hex 7 seg, our AN code, and our clock divider. So we'll make a new top level design here. We'll have the clock coming in. This should really be our M clock coming in. And then this component x7 seg B. So what we're going to do is we're going to set X to the switches concatenated with the lower 3 buttons concatenated with 0, 1, 0, 1, 0, 1. So digit 0 will always display A, and the upper digits you can control by the switches and the buttons, so you can make them leading zeros or not to test it out. So then to port map it, we'll just set X to X, clock to, this should really be M clock, clear to button 3, and the rest is all the same. So you can test that out to see if the leading zeros get displayed as blanks.